Hello and welcome back. We're going to continue with trees and particular tree traversal algorithms today for binary trees, of course. And then at the very end, we're going to transition into the next part of this module, which is going to be binary search trees, where we actually utilize these tree structures that we've built to actually hold relevant data. Before we jump into the actual implementations, like I said the last time, we were going to do the actual implementations of preorder traversal, postorder traversal, inorder traversal. Here's our tree from last time, and I just wanted to remind ourselves as a review here of what those tree traversal algorithms look like. All right. So in general, if you've got a parent and you've got a child, I'll just call it U, and then that child has a left child and a right child. Remember that a preorder traversal visits it by going with the root. And by root, we don't mean the root of the tree, but we mean the root at that particular node. So in other words, this could be the root up here. But then when we traverse down to this child node down here, then that becomes the root of the subtree rooted at that node. So it's going to visit the root. It's going to process the root first, then go down to the left subtree. Then it'll after it's done processing the root, then the left, it'll go onto the right subtree. Okay. An in-order traversal visits it as left, then the root, then the right. So left, root, and right. And then finally, in a post-order traversal, and you can see the only difference between all of these is, again, the root. You go root first, then root in between, and then the post-order traversal is, of course, going to go left, right, and then root. Okay? So what we're going to do first is we're going to look at pre-order traversal. Okay? Now let's think about this generally, like I've got here with a parent, the current node that I want to process, and then a left child, right child. And remember that the left child, the right child may or may not exist depending on the topology of the graph. The topology of a graph refers to what it looks like, how things are connected together, the landscape basically of the tree. Remember, we do have Piazza going for live Q&A, so if a question does come up, please go ahead and post to Piazza, and I'll try to get to it. Okay? So the pre-order traversal, again, what we want to do is we want to think about how this works. We've come down to this this node U here. We've already processed everything up to it, and maybe everything over here on the right will eventually process that. But basically, I want to do a pre-order traversal here. I'm looking at this tree brand new. I'm looking at the tree as if it were the only thing in my scope, right? That as if none of this other stuff, none of its ancestors, none of its cousins or aunts or uncles exist. I'm looking at just this tree. Okay. To process the root left and right, well, the first thing I'm going to do is I'm going to process the current node, because that's exactly what I want to do with a preorder traversal. I want to process the root. Right? Then what I need to do is I need to go left and process the left subtree. Right? Go left. But I need to keep track of the breadcrumbs that got me here, because I need to eventually come back up here and then come back over and take care of the right subtree. Okay? So there are a couple of ways that you can do this as far as implementation is concerned. The first and most straightforward way is, of course, to use recursion, right? So if I go left and then eventually I come back, I'm returning from a recursive call, then I can just go right. And there is no but, right? However, the but here is that you went left and you processed the left subtree, right? So going left means process the left subtree. Right? Go right means process the entire right subtree. So this suggests an easily recursive algorithm where all you have to do is three things. You have to process the node, go left and process that entire subtree. Then after you're done with that, go right and process that entire subtree. Okay? So what I want to do now is I want to switch over to, let's see, main screen. What I want to do is I want to switch over to my Eclipse view over here. So today what we're going to do is we're going to go through all these basic Java implementations. We're going to look at recursive solutions for all three of these. Then we're going to go to a stack-based version of these instead, because what we want to do is we want to eliminate that recursion. Recursion is nice. It's very simple code, but at the end of the day, what it's doing is it's abusing the stack space. So what we're going to do is we're going to use our own in-memory stack anyway. This is why we introduce these data structures and algorithms. I'll talk a little bit about how you can generalize these to basic tree walks without using any data structures whatsoever. We won't necessarily implement those, but it is nice to know about them. And then we'll revisit that BFS walk where you're going top to bottom, left to right in each one of those levels. Okay. So here's my basic Java implementation. Here I've got a tree node. I mentioned this last time. And a tree node is kind of like a linked list node in that, but instead of having just a previous maybe and a next, it has a left child, a right child, and a parent. Okay. So, and also of course a value. We're holding things, and it's parameterized here along some parameter so that we can have a tree of strings or a tree of numbers or something like that. Okay. So here's my actual binary tree implementation. Right, we're not in binary search trees yet. We have not discussed that. So I'm just going to keep it simple as a binary tree. Right? All it has is access to one root node. If I kept track of all the nodes in the tree, then basically I have a list implementation, and that defeats the purpose of defining this this data structure. So what we're going to do is we're going to traverse this tree, and I'm going to show you several different ways of doing it. Preorder traversal, an inorder traversal, and a postorder traversal. And of course, we'll look at recursive versions of this and then non-recursive versions where you're utilizing a smart data structure instead. To help me out, I've already created a test case here. All I've basically done is I've created a binary tree with nodes A through R as strings here. I noted the preorder traversal, inorder traversal, and postorder traversal. And in case that you don't remember this, this is the one that I started out with. I built this tree programmatically so that B and C are the left child and right child of A. A has no parent, etc., etc. So the one that we practiced on last week, these are going to be the solutions. Okay, I just built this tree using the same topology so that we would have something to work with here. And if you look back at that lecture, then you see that the preorder traversal, the inorder traversal, and postorder traversal, I wrote those all down here so that we have a nice test case that we can say, okay, well, this implementation probably works because it works on this one test case. Right? Of course, you'd be if you were doing this for real, you definitely want this to be repeatable, and this is kind of like ad hoc testing. It's not a true unit test. Okay. So what I've done is I've set this up so that I'm traversing the binary tree, and the way that I give my answer is basically I build up a list. So if in a preorder traversal, I would add A to the list, then I would add B to the list, D, et cetera, et cetera. Right? Just remember here, a preorder traversal visits the root, then the left, then the right. So I would go A, then B, then D, then D, G, L. And then I would come back up. And there's no left child, there's no right child. So I come back up, I go M, and then R. Come back up, H, N, et cetera, et cetera. And so I've written all that down here. So A, B, D, G, L, M, R, H, et cetera. So that we can actually take a look and make sure that we are doing this correctly. Okay, there's the setup. So here's the traversal algorithm. Again, I want to start at the root here, and I want to do this recursively. Right? So this is not a recursive function. So let's define a separate recursive function here. Public, and oops, ignore that for a second. There we go. So public, I'll make it a void function for now, and I'll call it preorder recursive. Okay. So as I said, all we have to do is process the current node, then recursively go to the left child if it exists, and recursively go to the right child. So I'm going to need some inputs here. I'm going to need, well, what do I need first? I need to know where I am. So I need that current node. And so that's going to be a tree node, parameterized along the same value, the same type, excuse me. So current node. I'll just call it cur for current. Right. But of course, I'm not paying by the character, so I'll go ahead and call it fully current here. Okay. All right. So I'm also going to want to build this list here. So I'm going to go ahead and pass that through, and what we're going to do is we're going to continue to pass that through to each one of these recursive calls so that we can add to the end of it. I could have made this static. I could have made this a member variable. I could have done a lot of different things, but I'm just going to pass this through to my recursive call here. So now my first thing that I'm going to do is I want to process the current node. And by processing, we simply mean that we're going to process the node. We're just simply going to add it to this list over here. Okay, and we're not actually adding the tree nodes, by the way. Just like in a linked list in our implementation when we worked with that, if you wanted to get something, you never got the tree node, or you never got the linked list node. You actually got the thing that was stored inside the linked list node, and so that's what we're actually building up here. We're at a current node that might have a parent, might have a left child, right child, whatever, and we're taking the thing out of that node and we're putting it into this list. So that's pretty simple. All we need to do is result.add to the end of the list the current value. Right? At this point, let's go ahead and jump back to the tree node here and look at some convenience methods that I've built. We've got setters and getters for the parent, setters and getters for the left child and right child, respectively. But also I've got this convenience method here, has a parent, has a left child, and has a right child. And it's simply just returning whether or not the nodes that it's connected to are null or not null, and in which case they are valid, and so it does have a right child, for example. Okay. But also we've got this value here, which is set to be final, set in the constructor, which I've already taken care of in the main. I built that tree already. But we've also got a getter for it. So here's the get value, and it just simply returns the value. And that's what I'm using here. So processing the node simply means I'm going to get the value and then put it into a list so that I can give you the pre-order traversal. Okay? All right. So second thing that I'm going to do is I want to recursively handle, that is, traverse the left subtree. So what I'm going to do is I'm going to call this function again. That's what recursion is. You're calling the function, right? And I'm going to pass it the current's left child. Right? If it exists, we'll take care of that in a second here. And of course, I'm just going to pass through the result here so that I'm handing the list off so that future recursive calls can add their own things to the end of the list. I also recursively handle or traverse the right subtree. And so instead of getting the left child, I'm going to pass off the right child. Okay? Now, hopefully you see an error here. And whenever you're thinking about recursion, you have to remember recursion is basically a loop. With a loop, you have an initialization, a continuation condition when you stop this loop, when you terminate this loop, and of course you're making an iteration. You are making progress towards the termination condition so that you don't have an infinite loop. Here we basically have an infinite recursion. Actually, it'll probably end with a null pointer exception at some point. When we get down to the last node that has no children, right, we don't want to go to the left child. We don't want to go to the right child. In fact, in general, if it doesn't have a left child, we don't want to go to it. If it doesn't have a right child, we don't want to go to it. I could put these calls on line 26 here and line 28 into if statements that if it has a left child, then traverse to it. Otherwise, don't traverse to it. If it has a right child, then traverse to it. Otherwise, don't recurse to it. Or I could take care of that as simply with one case here of a base condition. Remember that what the thing that you need to do with recursion is you need a base condition, a stopping condition where you don't recurse anymore. you need to make progress towards that recursive, that base case, that termination condition, it's basically like a loop. Okay, up here, we haven't gotten to it yet, but that's going to be our initialization. How do we actually get this thing started? Where do we, what do we pass off first? Okay, but what I'm going to do, I want to take care of that base condition here first. If the current is invalid, in other words, it's null, then I've fallen off the edge of the tree, right? I've got down to a leaf. There is no left child. So what I end up doing is I end up passing null here. And on the next recursive call, I've got the current is null. And so I do nothing, right? We're past all the tree, so do nothing, right? Just simply, and in terms of Java, that means return, right? Okay. All right, now I need to kick all of this off. I need to call a preorder recursive traversal on this, passing in what as my first node and the result, which is an empty list, and then it'll get built up, and then eventually return that result. Where do we start? Well, the only place that we can start is the root. So this dot root. Okay. All right. I've already got it set up here so that we can traverse and it prints out the list that we get back. So let's see if this works. All right. There's the preorder traversal, A, B, D, G, L, M, R, H, N, E, I, O, U, C, F, J, P, Q, and K. So it looks like it works. Right? Great. A nice little recursive function here, a nice little recursive method. It definitely has a stopping point. There are some corner cases you need to think about, but it's probably taken care of by like this. For example, an empty tree or a tree with only one node. You definitely want to test those out in any formal testing suite. But I'm pretty confident that this works. So what I'm going to do is I'm going to collapse this, and now I'm going to think about an in-order traversal. Okay. So let me go ahead and transition back over here. And remember what happens with an in-order traversal. An in-order traversal, you don't process the node right away. Instead, you go to the left subtree and process the entire left subtree before coming back and processing A. You process the entire right subtree after that. So in other words, left, root, and then right. That suggests another recursive solution here. Right? So I'm going to go ahead and copy the contents of this, and I'm going to call it an in-order traversal instead. All right, there we go. We're still going to take a current node. We're still going to take the result because we want to build up this list. And we still want I'll go ahead and remove my notes here as we go along. We still want a base condition here. If we've fallen off the edge of the tree, then we don't recurse anymore. But instead of going with the root, then the left, then the right, what I'm going to do is I'm simply going to change the order that I process it and go to the left, then process it, then the right child. And of course, I need to make sure that I am calling the correct recursive version here. And up here in the traverse, I'll change my traversal algorithm here to be an in-order recursive version. Let's see if that works. LR, oops, I think I just copied, cut and pasted that wrong, or typed it wrong. LGR, then let's see. Yep, L, then G, then R, then M, D, H, N, B, E, O, I, A, C, P, J, Q, F, and K. All right, great. And of course, you can now see the pattern of, well, if that's how you do it, all you have to do is change the order of your calls here. Then what does a post-order traversal look like? Of course, change the recursive calls here. And instead of going left, root, right, we go left, right, and then root at the very end. Okay? And let's go ahead and call this and see if we get that result down here. So a post-order traversal would have still L as the first one, but of course now the root of the entire tree A is all the way at the end here. Let's see if that works. And that's exactly what we get here. Quick visual inspection, looks like it was correct. Okay? All right. Well, seems on the surface like a strong argument for recursion, right? Nice, simple code. Nice, elegant, simple code. Elegant, simple, these are subjective terms, right? It is definitely simple, but you're abusing the call stack to do this, right? And so is there a way that I can achieve the same thing without abusing the call stack, without using recursion? Okay. Now what I want to do is I'm going to transition back over here and let's go over an example. In fact, if you think about the call stack and how it's working, basically it's leaving breadcrumbs. It knows that, okay, well, I'm here and I'm going to process that node, then I need to go left, then I need to go right. The returning back from that function are your breadcrumbs. Eventually, you go from A to B to D to G to E. That's your call stack right there. What if instead of abusing the call stack to do that, what if we just put those into an in-memory stack? Okay. What I mean by that is, here's a stack. In fact, let me use a different sheet of paper here so that... Here's a stack. Now, I start at A, and this is where I currently am, okay? So I'm going to process A. Before I process it, what if I put it into a stack to keep track of where I've been, right? So A is going to... Now I immediately take this off of the stack and I process A. So process A. And it's no longer in the stack. Now I could jump immediately to the left subtree, but I need to keep track of where I've been. Eventually, I'm gonna do the entire left subtree here. I need to come back so that I can do the right subtree. So to keep that in mind, to keep that in memory, what I'm going to do is I'm going to push that onto the stack, C. Right? Then I'm going to go down to the left subtree by pushing it onto the stack, B. Okay. Now, this is not only just breadcrumbs, but it's also telling me that you need to process C, but before you do that, you need to process B. Okay, what I'm going to do is I'm going to pull the thing off the top of the stack, process it, and then repeat. I'm now at B. I just processed it. So I need to remember, I need to come back to E, but before I do that, I need to process D. And then I repeat that process. I take the thing off the top of the stack, process D, and now I'm at D, so I push H, and I push G, and then I will continue. I'll process G. That's keeping track of all the stuff that I eventually need to come back and process. It's keeping track of it in one stack, though, instead of abusing the call stack to do my work for me. Right? So let's see what that looks like. Okay. Let me go ahead and create another method here. Public. Let's go with list t. No, we won't return the list. We'll take the list. So let's go with a preorder stack traversal. This is not going to be. I should say that this is not going to be recursive. Let's go ahead and give our list to it, though, so I can keep the same pattern up here. Okay. Let's see. No questions so far. I'm going to pass through this list and I'm not going to start at the root because I'm not passing that in here. And that looks good. Preorder. There we go. Oh, and it's a void. Sorry. There we go. So there. So now if I just ran this, of course, it would give me an empty list. Right? So I'm going to have use a stack first of all. So let's create a stack. Stack. And what's it going to hold? It's going to hold tree nodes that are parameterized along a type T. Okay, and I'll just call my stack S. There. Now, how do I get everything started? Well, I start at the root. So I'm going to push the root on top of the stack. This is the initialization, much like that initial call up here that I've now replaced with traverse. That initialization, you got everything started by starting at the root. I'm going to push the root on top of the stack. Then I'm going to continue that. I end this this entire process when the stack is empty, right? When I've processed everything, I've processed everything in the stack. It's now empty, so I'll go ahead and quit. So while the stack is not empty, then I will continue to process, okay, and then ultimately return at the end, okay. Now, in the example that I did over here, the first thing that I did is I pulled the thing off the top of the stack. The stack are my breadcrumbs, and I need to pull off the thing on the top of the stack because that's my current node. So tree node t, and I'll call it current, is equal to p dot, and then to take something off the top of the stack, it's going to be pop. Okay. Oops, s.pop. Now, I'm going to process it, and by processing it, it's just exactly the same as before. We're going to add it to our list, right? Get that value. But now I need to set myself up for the next the next iteration. Instead of the next recursion, the next iteration. I'm at the current, and I've got a left child and a right child. I want to push that right child first, and then the left child. So s.push current dot get right child, and s.push current dot get left child. Now remember that a preorder traversal is root left right. So why do I push the right one first before the left one? Because remember, a stack is a LIFO data structure. The last one in is the first one out. So you need to push things in the reverse order that you want them to come out. So if I want to go left first, I need to push the right one first so that the left one ends up on top of it in the stack. Now we do need to make some considerations here, because if there is no left child, if there is no right child, obviously I don't want to push them onto the stack because I would be pushing null onto the stack. And when I pull it out and I try to get its value, then I'll have a null pointer exception here. In fact, I can show you that. Let's go ahead and try it. Preorder stack traversal. Let's go ahead and run it. There we go. I get a null pointer exception because I'm not handling those corner cases. So what I want to do is I want to make sure that I only push the left child if it actually exists. So if the current has a right child, then I do this. Right? If the current has a left child, then I push the left child. That'll take care of my null pointer exception here. And it's exactly as before. A, B, D, G, L, M, R, etc., etc. And you can visually see that that's the same. Now, again, some people would argue that the recursive version of this, let's see, where is it? The recursive version is more elegant because, it's only 3 lines of code once I get rid of all my comments. 4 lines if you count the base condition here, right? And it's fewer lines of code, yes, but fewer lines of code is not necessarily more elegant. It's not necessarily even more simple, right? And that's why I like to cover both of these, because anything that you can do with recursion, you can do away with the recursion with a simple stack, okay? And this is really, really easy to do. All you're doing is putting stuff in and taking stuff out. You're using a smart data structure to exploit. You're exploiting a smart data structure and its LIFO nature, the last in first out nature, in order to solve a problem here. Right? So you're using the smart data structure and you're making the data structure do all the work for you. Really, all you're doing is taking stuff out and putting stuff in. Push pop, push pop. Just the taking care of corner cases and getting the right sequence down is all the thinking that's required here. Okay. Now, I would agree with the argument that it gets a little bit more complicated if you're going to do an in-order traversal or a post-order traversal non-recursively. But nevertheless, we are going to check it out and see if we can do them. Just to make sure, I do have my book here. This is a pseudocode on how to do the in-order tree traversal. And what we're going to do is we're going to take this pseudocode and we're going to translate it to Java code. If it's good pseudocode, then we would be able to translate this to any programming language medium, okay? Any programming language that we want. So public void Inorder traversal, or Inorder stack traversal. And I'll use the same signature here. We're going to hand off the list, add to the list as we go along, and then ultimately return it. Now, I do have comments here that are going to describe what's going on, but before we do that, let's go ahead and transition back over here to my overhead. And let's understand how this was designed to begin with. How are we doing an in-order traversal with a stack? So here's our current node. And we've got potentially a left child, we've got potentially a right child, okay? And of course, we might have come from a parent. If we're the root, then we didn't come from a parent. But I'll go ahead and draw it just in case. So understand how an in-order traversal works. If this is the first time that we've come into this node from the parent, then we don't want to process it, right? If this is the first time that we've come down from the parent, then we ignore it. We don't process it because we want to process the left tree, and then we want to eventually process the right subtree. Okay. So we don't process it. Instead, we save it. And the way that we're going to save it is by pushing it into a stack, so that eventually, when we come back up, then we'll see it, and okay, now I process it, and then I go down to the right subtree. Okay, so we save it, and then we go to the left subtree if it exists, of course. Okay. Now the second time that we've seen this means that we're coming back from having processed this entire left subtree. So now we do need to process it, because an in-order traversal goes left, then root, then right. So we process it, and then go to the right. And then, of course, that'll be the first time that we've seen that node, and so we don't process it, we save it, and we go off to the left on that subtree there. Right? So all we need to do is distinguish two cases. If this is the first time that we've seen this node because we've come down from the parent, or is it the second time that we've seen this node because we're returning from the left child? Okay. That's what this pseudocode over here does. Right? We start with an empty stack. We initialize, we keep track of the current variable here, or the current node, I should say. In the pseudocode, I called it in the actual code here, I'll go ahead and call it current. While the stack is not empty, or you have not processed this node, because eventually the stack is going to be empty, and you're still going to have a current node that you need to process. Okay. So it's a little bit different from preorder traversal, a little bit more complicated in that we've got now two cases. Before, we didn't have any cases at all, right? The preorder traversal, we just did the same thing every single time. There was no if here, other than if to check to see if there was actually a child in order to push it or not to push it. Okay. So we have two cases here of distinguishing whether or not we came down from the parent or are returning back from the left child. So let me go ahead and set ourselves up here. The first node, the first line of code here, we just initialize an empty stack. We'll start at the root, so tree node t, and I'll call it current. Of course, it's called u over here, and I'll initialize that to this binary tree's root. Okay. Now I've got a while condition here. While s is not empty, sorry, or u is not null. And one of the reasons for it's current. One of the reasons for this also is if we've got an empty tree, this takes care of our an edge case. So if it's an empty tree, then it will be null, and so we never actually execute this while loop, and then ultimately we return an empty list here. Okay. If u or current is not null, then we do one thing. Otherwise, we do another thing. So again, the comments here tell you what this is, what we're doing. If the current node is valid, then we push it for later processing. Remember, this is the first time that we've seen it, and we don't want to process it because we want to process that left subtree before coming back to it. Okay, so s.push u, and also we need to now go to the left child. So current, it will be updated to current's left child. All right. Now, otherwise, the other case is where we're coming back from the left child. So otherwise, we're returning from the left subtree. So we remove u off of the top of the stack and we process it. So tree node. Actually, I could reuse current. Current is equal to s.pop. Oops. Haha. We process it, and that simply means we take result dot add current. But we don't want to add the tree node. We want to add the value stored in the tree node. And so we add that there. And then we end up going to the right subtree. Again, we've processed the left subtree. We've processed the root. And so now we need to go on to the right. So current will end up being current.getRightChild. Now, the nice thing about this implementation is that I don't think that I have to check to see if there's a left child or a right child like I did with the preorder traversal. Before I pushed them, I had to check to see. I end up pushing null here, but I do null pointer checks over here, right? If the current is not null, that's my flag indication that I've come from a parent. If it is null, then that means that I'm returning from the left subtree, and so I need to get the thing off the top of the stack. So since I've incorporated that into my algorithmic logic here, I don't have to check to see if the left child or the right child exists in order to push it. Push right here. Okay. Let's see if this actually works. Oops, I need to change my traversal to an in-order traversal. And so here's the in-order traversal again. I'll expand this out, get myself some more room. And let's run this and see if we get that in-order traversal. L, G, R, M, D, H, ... all the way up to K. Looks good to me. Very nice. Very elegant. Again, that's going to be a subjective take on what code looks like. This is very beautiful code to me. Somebody looks at a recursive version and says, oh, that's very beautiful code to me. I look at a recursive version and I say, recursion, ew, gross. Let's go ahead and get rid of it. Let's use a smart data structure instead. Okay? Now, you do definitely have an even more of a strong argument that you should probably use recursion if you were going to do a post-order traversal. There's the pseudocode for it. And we can go through this. Let's see. We've got plenty of time. We can go through this. And I don't think that I do this in any of the other videos. So we can go ahead and translate this pseudocode over to Java code. Let me go ahead and set myself up for it. And then we will come back and so in order post-order traversal. I'll set myself up for it, and then let's understand what the other cases are. So let's come back over here. So in in-order traversal, you had to distinguish whether or not you came from the parent or came from the left child in order to say, the first time I don't process it. The second time I do process it. What does an in-order traversal look like instead? Or sorry, a post-order traversal. A post-order traversal would actually have three cases. So here's the current. We came from the, say, the parent. We have a left child or a right child. Now we've got three cases. Is this the first time that I've seen it? Or after processing the entire left subtree, I come back up. And is this the second time I've seen it? That's exactly the same as with an in-order traversal. But with a post-order traversal, we explore the left, then the right, then U. So we need to also distinguish between whether or not it's the third time we've seen it. And the third time is when we actually process it. The first time and the second time, we just need to make sure that we can be able to we're able to distinguish those. All right. So we'll still be pushing it onto a stack, but we need to make sure we'll have a second check here, right? So we'll push U for later processing, and then we'll go left. if this is the second time, how do we even actually determine this? Well, we're at U if the previous node that we came from is use left child, then that means that we came up from the right. The third time that we see it is when we come up from the right child. That's the third time. That's when we actually process it. All we need to check is, well, this is our current node. This would be our previous node. Is the previous equal to the current's right child? And that's the trick. We're going to keep track of not only a stack of where we've been, breadcrumbs, but also we're going to keep track of the most of the previous nodes. We're at the current node. We need to keep track of a previous node. Did we come from the parent, or did we come from the left child, or did we come from the right child? That gives us 3 cases to be able to distinguish. Okay? I'll go ahead and transition back now to the Java code and make sure that we're actually going to call this. There we go. All right. So here's the pseudocode. Let me bring it over here. There we go. Plenty of room here. Just check in. No. Oh, here. There is a question. What potential problems do we run into using Java's call stack that can be avoided with its own stack? Good question. The call stack, it may not be very deep. In fact, we can test how. In fact, that's how we tested whether or not one of your functions was recursive in one of your labs. We wrote a JUnit test to see how deep the stack was, and then we forced a Stack Overflow by making that many recursive calls to see that you were actually doing it recursively instead of non-recursively. I think it was the palindrome one in the recursion lab. That's how we tested it. So we forced a Stack Overflow by calling the function over and over and over again. And that's the risk. The risk is that you would end up having a Stack Overflow, that you're abusing memory, that pushing and popping of stack frames, that costs you something. Whereas an in-memory stack is only bounded by as much memory as you have in the virtual memory space, or as much as is allocated to the Java virtual machine. The stack space is typically much smaller, though. I don't remember how much it is, but I think the default default on CSE at least is like 4 megabytes. And so you could call like 4 million recursive calls or thereabouts, on that order. But that's it. You're risking Stack Overflow. Right? That's the issue. Okay. But again, for most, that means that you have a tree that is 1 million levels deep. For all practical purposes, it's not that big of a deal. But if you're in an embedded system, it absolutely is a big deal, where your stack space might only be a couple of K instead. But if you're in an embedded system, you're probably not. Java is a huge memory hog. So you can set up Java to restrict the stack space up front, and you can run it on embedded devices. In fact, Java was invented for embedded devices. It was originally developed and written for cable box tops, I believe. All right, so let's go ahead and go back over here to the pseudocode. Like the others, I'm going to create an in-memory stack here. Right? That can be several gigabytes by default. Right? I'm also going to keep track of a current and a previous. Right? So this one I'll call previous. Right? And this .root. I initialize that. Oops, sorry. I need to initialize that to null. Right? And then we're going to push the root on top of the stack. I've translated these first 3 lines over here. And now you can kind of see the utility of writing pseudocode. If you write pseudocode and it's clear, well-written pseudocode, you can go ahead and translate that to any other language that you want. If you're a Python person, you should be able to see that. Oh, previous, I can set variable prev equal to nil or whatever, or null. They do have null in Python. And you've got a stack implementation. Every language is going to have basic data structures like this. So just translating it over, usually if it's well-written pseudocode, it's going to be almost virtually a line for line translation. So again, while s is not empty, while it's not empty, that's why I'm putting the not in front there. Then I'm going to establish the current node. But do not remove it from the stack, because we'll eventually need to process it after we've done the left subtree, after we've done the right subtree. So what I'm going to do to achieve that is I'm going to peek at it. Remember that the peek operation, and it is supported by the Java stack here, gets the element at the top of the stack, but it doesn't remove it, right? It just takes a peek at what's on top of the stack, right? We will eventually remove it, but not immediately. Right? Now we need to determine if this is the first time that we've come to this node. In other words, did we come from the parent? So I'm going to have an if statement here that is going to check to see whether or not the previous is null, or the previous's left child. Oops, sorry. Thought get left child is the current, or the previous dot get right child is the current. So I'm going to break this up here and bring it down to the other line so that we can look at all three of these things together. What is this doing? Well, if the previous is null, in other words, we came from a parent that was null, or the previous, the one that we came from, is its left child is us, right? Or the previous right child is us, then that means that we came from the parent, right? There's an old mind teaser. Brothers and sisters, I have none, but this man's father is my father's son. Who am I? Well, I am me, right? It's kind of self-referential. If the thing that we came from, if its left child is the current, then that means that we came from the parent. Previous, current. So if the previous's right child is us, then that means that we came from the parent. Previous and current. Right? Or if it's the left child. Or if it's the root and we came from nothing, right? We just simply started here. So at this point, we came from the parent. This is the first time we've seen current. Okay. Let me give myself some more room temporarily here. All right. So what do? We push the left child if it exists, because we need to go to it next. So if current has a left child, then we push the left child of current. Otherwise, the current has no left child. So in other words, it has a right child. It may have a right child. If it has no left child, then there's nothing to go to. So we don't end up going there, right? So we do need to check to the right child, right? Because we do go left, right, root. And so if it has a right child, we need to process that first. So if current has a right child, then we push it. And this is an either or. This is an if-else-if statement here. These are mutually exclusive, because either it has a left child, and so I need to go to that and take care of that. Eventually, I'll come back up and then check to see if it has a right child. But if it has no left child, then I don't need to do any of that stuff. I just need to immediately jump to the right child. Right? Otherwise, do nothing, as we'll process the current node below down here. Okay. Otherwise. So that's the first case. Else if the current dot get left child is equal to the previous, then we came back up from the left subtree. Okay. Let's just go ahead and check in here. Okay, good. So this is the second case. Again, the first case is we came from the top, we came from the parent. The second case is we came from the left child. The third case is going to be that we came from the right child. So how do we know that we came from the left child? Previous is current. We came back up. Now current, we're at this node. We came from the left child. In that case, what we need to do is check to see if the right child exists. And if it does, then we need to process, or then we need to push it so that we eventually process it. Okay? And that's just going to be a repeat of what was up here. Okay. Otherwise, else, the third case is we came back up from the right subtree. In which case, we're done. We didn't come from the parent. We didn't come from the left child. We came from the right child. In other words, we processed the left child or the left subtree. We processed the right subtree. We're done with left, right. Now we need to do root. So we process the current. And again, by processing, we're just simply adding it to our list. Current dot get value. There we go. And we take it off the top. Remember, we only peeked at it to see what it was, to see what we should be doing. Should we be going left or right, or where did we come from, basically? And so I just need to remove it now. And you don't need to capture that or anything like that, since we've already got current over here. Now we update where we came from for the next iteration. This is we're still within the while loop here. Previous is going to end up being the current. All right. Again, we're at the current. We go on to some other node. We either go down to the left child, we go down to the right child, or we go back up to the parent. We need to keep track of where we came from. So the current, that ends up being previous. Just like with our linked list implementation, for some things we wanted to keep track of the previous and the current, so that if we ever need to insert something in between them, right, we had access to the previous and we had access to the current, so that we didn't have to start all the way back at the beginning or go back one if we supported a previous element in our linked list. As always, we need some testing here. So let's make sure that this still works. Oops. All right. LR, it's looking good so far. Here's a post-order traversal, LRMGN, H, D, O, etc., all the way over to A. Excellent. Right. Good pseudocode. Right. Very complex. And here you do have to say, oh, it's 20 lines of code. If you're a lock person, LOC, lines of code, we need to simplify this. Go ahead and just use recursion. Okay. And then when the stack space is abused and overflown, then come back to me, because I've got a better solution. In fact, I have an even better solution. No recursion and no data structure at all. Right? So to understand that, let's come back over here. And think about what you're doing here with preorder, postorder, and inorder traversal. These are all basically what are called depth-first search. We're going down as far as we can into the graph before coming back up. Breadth-first search, which we talked about before, and we will revisit that, visits things that are immediately adjacent. So it's kind of like a radial pattern here. It visits things that are closer to the root before it visits things that are deeper and further away from the root. But basically what you're doing with the depth-first search on a tree is you're taking a walk around the tree. You're going down to the left subtree first. Now, there is no left subtree. There is no right subtree. So what do? You come back up. Right? And then you come back down over here onto this side. And then once you're done with this, there's no left subtree, no right subtree. You come back up. You come back up. You come back up. Basically, you are taking a walk around the perimeter of this tree. Right? It's called a tree walk. Right? And in general, all you need to do is keep track of two things. You don't need a whole stack to keep track of, when to process this. You only need to keep track of two things. Here in general, if I've got a parent, the current node, a left node, and a right node, like I did with the last implementation, the postorder traversal, I just need to distinguish three different cases here. Did I come from, right now, here's my current node, current. Did I come from my parent? In other words, previous node is equal to the parent. And let me give another piece of paper here. So the previous is equal to the parent. In other words, I've come down from it. Otherwise, if I'm coming back up from the left child, that means, or I'll draw it like this, right? Since that was the tree walk that I did. I'm going around the parameter of the tree, or perimeter, excuse me, not parameter, perimeter of the tree. So if the previous is the left child, or the previous could be the right child. and I've come back up from the right child. Right? Then where do I go next? Well, if I came from the parent, where do I go next? Go to the left. Right? Because if I'm doing this tree walk over here, I go left, 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 left until I can go left no more. Right? And of course, there are corner cases here that you have to be aware of, where these might be null. Right? So you don't want to jump off the end of the tree. In general, you just want to rearrange and say, well, now instead of going down to a non-existent left child, I'll just say that, well, now my current is equal to the previous, and there are tricks to do that. Otherwise, if my previous is the left, then that means that I need to go right. Right? Because I'm coming back up, I've processed the left subtree, and so now I need to go down and process the right subtree. Otherwise, if my previous is right, then I go to the parent. And that's how I do a tree walk. A tree walk is very, very simple. All you need to do is distinguish between these three cases, and it tells you where to go next. Not only that, but a tree walk can be used for all three of the preorder, inorder, or postorder traversals. All you need to do is tell, well, here's my current. Did I come from the parent? Well, that corresponds to a preorder. Process if it's a preorder. Let me move this over. Otherwise, if I'm coming back from the left, then all I need to do is say, well, I'll process it if it's an inorder. Because I process the left subtree, now process you, and then go on to right. Right? Because that's what I'm going to do. I came from the left, I need to go right, but before I do, I process it if it's an inorder traversal. And if I came from the right, then I process it if it's a postorder traversal. Right? So you can actually achieve all three of these things with no data structure whatsoever. It's a very simple tree walk. All you need to do is keep track of two things: the current node and the previous node, where you've been and where you are. And that tells you where you're headed, and it also tells you whether or not to process the node depending on one of the three things, whether or not you're trying to do one of those three orderings. Right? I'm not going to implement that. But there is a pseudocode implementation available in the book. Instead, what I want to do is I want to do a breadth first search traversal. So let me go ahead and create one more function here, or method, BFS traversal. And we'll take this list here. There we go. And I will change this so that this is BFS. And I didn't even bother writing it down because the nature of the tree that I wrote, it's going to be alphabetic. If this is successful, then it's going to be A, B, C, D, E, F, G, etc. Again, let's take a look at this tree that I've got here. You're reading top to bottom, left to right. So A, then B, then C, then D, then E, then F, then G, H, I, etc., etc. Right? So if testing on the same tree over here, if our BFS is successful, then we don't even have to write it down here. It's just going to be in alphabetic order. Okay. Now let's go ahead and transition back over here and let's figure out how to do this. There we go. So the first thing that I want to process is A. Right? Then I want to process B and C. Okay. Then I want to process D, E, F. Right? And as we would expect, this is going to be the order that I just said. What kind of data structure is this calling out to you? Right now, one of the bad things about remote learning here is that I can't ask Socratic questions, and we don't have a Socratic interaction here. But hopefully you can think about this. That if I drew it like this instead, and I said that tree nodes came in here, and then they went out here. This is they're lining up, right? This is a queue. Right? That if I start at A, put it in one end, and then take it out the other end and process A, right? It's no longer in there. I need to keep track of, well, next I'm going to process B, but also I want to process C. I don't want to forget about that. Right? All I need to do is NQB and NQC. in that order. Left child first, then right child. And then I repeat the process. I dequeue whatever is over here, process B. And then that's now out of the queue. C, or now B here, I look at its children, D and E. And I enqueue those left to right because I'm going top to bottom, left to right. Right? So this is going to be very, very simple code, very, very similar to something that we've already done. In fact, I'm going to pull what we've already done here. Oops. With the preorder stack traversal. I'm going to put it in my BFS traversal. And I'm going to make changes to it. Now it's no longer a stack, though. It's a queue. Queue is deprecated, so what I'm going to do is I'm going to use a deck. Right. There we go. Remember that a deck that is a double-ended queue, so that you can treat it like a queue. You can put things in at one end. You can take things out of the same end. You can put things in and take things out of both ends. Right? Double-ended queue. And it will go ahead and use a linked list implementation. And of course, I'm going to have to import all these. Deck and deck. There we go. And I'm not going to push it. Instead, what I'm going to do is I'm going to... it would be really nice if they used what I prefer, enqueue the operations. But a deck operation is simply going to be... what is it? Offer. Right? And we're going to offer this route. Right? That's how we set ourselves up here. Let's go ahead and refactor this. It's going to be a queue, so I'm going to treat it like a queue. I'm going to name it appropriately. That it's going to be Q instead of S. Right? So we offer it, we enqueue the route. While the queue is not empty, I'm going to pull out the next node. So that would be dequeue, right? But of course, there is no dequeue operation with a queue in Java. Instead, it is the opposite of offer is pull. Right? You offer at one end, you pull at the other. Okay. Then I add the result. Now I look at the left child and the right child. In other words, I change the order. If the left child exists, then go ahead and not push it, but offer it. If the right child exists, offer it. And then you ultimately return. So let's go ahead and run this and see if we get the result. A, B, C, D, E, F, G, all the way up to R. So it works. But damn, is that elegant. Right, look at this. Right, this is one of the themes of this course. In fact, I like this so much. Let's see. Compare with it. Can you compare with itself? Nope. Unfortunately, no. What I wanted to do is I wanted to do like kind of a diff here, but that's all right. We can here online diff tool. There we go. So I'll put the preorder traversal over here, and I'll put the BFS traversal over here, and let's go ahead and find the differences. Now the differences here, unfortunately, are many. It thinks that there are many, but they're kind of superficial. Actually, they look superficial, but it's actually hinting at a much deeper truth here. The only difference here, side by side, is that I used a queue versus a stack. Otherwise, I took things out, I popped it or I pulled it, I processed it, and then I put things in. But I put them in just in the reverse order because one's a LIFO, last in, first out data structure. The other is a first in, first out data structure. So, of course, I would need to reverse those. I'm pushing the right child, then the left child over here. I'm pushing the left child, then the right child over here. Right? It's same exact code, though. Right? The only thing that's different, really, from a substantive point of view, is the data structure I've used. Remember, one of the themes of this course is a quote by Eric S. Raymond, that a smart data structure and dumb code are a lot better than the other way around. This is smart data structures, stacks and queues, LIFO versus FIFO, first in, first out. The behavior is encapsulated in the data structure that you're using. Otherwise, it's the same exact stuff. You take stuff out, you put stuff in, you take stuff out. You put stuff in, you take stuff out. It's the data structure that is doing all the work for you, right? and the ability to recognize the appropriate data structure with the appropriate properties to use to solve a problem, it makes all the difference. Right? That's the difference between a real computer scientist and just a coder. Right? Being able to see when you do when you need to use a queue versus a stack versus a deck versus whatever. Right? Leveraging the power of these data structures in order to solve problems immediately. That's also a staple of like competitive programmers. Competitive programmers will be able to solve something immediately because they see the problem and they're able to map it to a data structure and then use an off-the-shelf implementation of that data structure like we did here in order to solve the problem immediately. Right? They're relying on the data structure implementation to take care of all of the grunt work for them. Right? But that is, again, one of the themes that I like to impart on this course. Smart data structures and dumb code. Dumb code being put stuff in, take stuff out, put stuff in, take stuff out, are a lot better than the other way around. Okay? All right. With only about 5 minutes left here, what I want to do is I want to give you a preview of next time. We have not fully exploited tree data structures here. Right? So tree data structures ultimately hold stuff. They hold the key. Here they're just holding a bunch of string values so that we can play around with them. But ultimately they're going to need to hold stuff, say student records or dictionary entries or something like that. Whatever you're trying to process, whatever you're storing in your tree. We're going to want some order here. So if we look at this from the perspective that a tree node holds a key value, and if we put on two restrictions, that everything in the left subtree is less than the key value, and everything over here in the right subtree is greater than the key value, then we're putting an additional structure onto our tree. This is already a binary tree because it has at most 2 children, but now it's going to be what's called a binary search tree. And by the way, this property has to hold for every single node. Everything in the left subtree is going to be less than it. Everything in the right subtree is going to be greater than it. This should sound familiar. This should sound very much like binary search. That if you look at the middle element here, everything, and this is k, everything over here is less than k, everything over here is greater than k because it's sorted. Binary search allows you to exploit this using random access, because you can jump in here to the middle element and say, oh, that's the thing I'm looking for, I got lucky, we're done. Or I know that it's in the left half of the list because the thing I'm searching for is less than k. Or I know it's in the right half of the list because the thing I'm searching for is greater than k. In either case, I've cut down the size of the number of elements that I still have to continue to search, binary search, in half. We couldn't do that with a linked list because you don't have random access with a linked list. You can't jump to the middle of a linked list because you have to start at one end, either the tail or the head, and then traverse all the way to the middle. But a binary search tree combines the best of both worlds here. We don't have random